Assalamu alaikum students. Hopefully every one of you is doing great in this course. Today we are going to start a new topic which is discrete Fourier transform. It is chapter number 8 of your textbook. Before starting today's topic, I want to ask a question from you. I want to ask, let's suppose we have a Fourier transform of a signal h of e raised to power j omega, which is depicted here. My question is, if you want to save it in your computer, how much memory will you require? Few bytes, kilobytes, or few megabytes, or more? This is my question. This is a Fourier transform of a signal, and my question is, how much memory do you require to save this spectrum in your computer or in your hard drive? One thing I want to share with you, that students of UET during 1980s were used to have a floppy disk in their bag. That floppy disk had a memory of 1.44 megabytes only. When I was a student, I had my USB which has 64 MB capacity. Now, I guess all of you or most of you have a USB stick in your pocket which is around 64 GB, or even some of you have more capacity USB. So is your USB sufficient to store this image or store this Fourier transform? So maybe you say it only requires few KBs because it's a simple image, but do you know your computer do not understand continuous signals? It works on 0 ones. Actually, I think your 64 GB USB stick is not enough to store this Fourier transform. Even if you have a terabyte of hard drive, this will not even sufficient to store this image. Now why? Because if you take only 9 samples of your Fourier transform, you will have this image. 1 sample, second, third, fourth, fifth, and so on. This is not even close to this Fourier transform. Here you have lot of samples which are connected by the computer. But how many samples? We don't know yet. So if we increase the number of samples from 9 to 21, your spectrum will look like this. Still, it is not close to original Fourier transform. So let us increase more samples. So if you want to store this, and let's suppose each sample requires 4 bytes in your computer, because a float data type in your computer requires 4 bytes. So if you have only 9 samples, this Fourier transform will require 9 into 4 bytes. Okay, here even a floppy drive is sufficient to save it. But here you will require 21 into 4 samples or bytes to store this image in your computer. but still you don't want to save it because it is not close to original Fourier transform, which is this one. So let us increase more points, and let's suppose it is we have 629 samples, and if each sample is taking 4 bytes, this sample can be saved in using few kilobytes of your memory. Okay, it is sufficient, but still it has some information missing, because if you have a value here, let's suppose it is 1.2, and you have another point which is 1. Let's suppose 7, then there are infinite points between these two time indexes or frequency indexes, because we are talking about Fourier transform. The x-axis is omega, and it is plotted between 0 to 2 pi. So if you increase more number of samples, say here it is around 6 million samples, and it will require around 6 to 7 MBs in your computer hard drive. But the problem is, you are saving the samples of this Fourier transform, which is actually continuous, but you are saving its samples. So let's suppose it is your axis, and it is a point 0.1, and there is another point which is 0.2. For continuous axis, if your axis is continuous, there are infinite points between these 2 points. No matter how close or how many samples you take, there will always be some information missing. For example, this is 0.15. Between this 0.1 and 0.15, there are still infinite samples. So if you want to store this complete spectrum, which is continuous in frequency, you need infinite memory if you want to completely save it, because in continuous axis it is from 0 to 2 pi actually, but between 0 to 2 pi there are infinite samples between 0 to 2 pi, and in order to save each sample you require infinite memory. So even your 4 terabyte of hard drive is insufficient to store this image. What MATLAB does is it takes samples and it joins those samples. Here you have only 21 samples. MATLAB tried to join them, but it is not even close to your original spectrum. So if you increase the number of samples, you say your spectrum is close to continuous time spectrum, but still it has this much samples. Between any two consecutive samples, there are infinite samples that you are not drawing here. So in order to completely store this waveform, which has range of 0 to 2 pi, but between 0 to 2 pi you have infinite number of samples, you require infinite memory. So it is a problem. You want to store the Fourier transform of your signal in your computer, but you don't have enough memory. You have even limited memory. In your computer you have around 4 terabytes of memory. Some of you have 4 terabytes of hard drive, but in your cell phone it is around 4 GB. But in your embedded systems, sometimes this memory is even in few megabytes. So if you want to store your Fourier transform in your embedded system, you have only few megabytes of memory. So how can you store it? So before giving you the solution, let me summarize what you have covered in this course and what you have already studied in your signals and systems course. After then I will give you a solution how can we store this Fourier transform in a limited memory. So in signals and systems course you have studied Fourier series. For a continuous time signal you have a periodic signal in time, whereas your Fourier series was aperiodic. Similarly, you studied discrete time Fourier series, in which you calculated Fourier series of discrete time signals. In that case, your discrete time signal was also periodic in time, like the periodicity present in continuous time. That is, you take Fourier series of continuous time signals. So in the case of discrete time signals, discrete time periodic signals, your Fourier series is also periodic in frequency. If your discrete time signal has period n, your frequency or Fourier series of discrete time signal has also periodic with n. So if you have aperiodic signals, then you calculated Fourier transform. You have studied it also in signals and systems course. There you saw if you have a continuous time signal which is aperiodic in time, its Fourier transform was also aperiodic in frequency, and the spectrum was continuous in frequency, whereas this Fourier series is discrete in frequency. For continuous time signal it is discrete in frequency. For discrete time signals, Fourier series is discrete in frequency, whereas your Fourier transform is continuous in frequency. And as well as if you take the Fourier transform of discrete time signals, which we have done in this course in chapter number 2, your spectrum is continuous in frequency, but it is periodic with period 2 pi. Like this is a discrete time Fourier transform. It is periodic with period 2 pi. This point is 2 pi, and this spectrum is continuous in frequency. So in digital signals or discrete time signals, you have Fourier transform which is continuous in frequency and it is periodic with period 2 pi. And the problem is that I have just mentioned, you have to store this Fourier transform, discrete time Fourier transform, into your memory. So the one solution is you sample this Fourier transform as you sample this Fourier transform in frequency as omega is equal to k omega naught. Then you will get a discrete Fourier transform h of k. Actually, you can also get this discrete Fourier transform from Z transform by using or sampling at Z is equal to e raised to power j k omega naught. This is the same sampling, but it is in frequency. You have studied in chapter number 4 that you can get samples by sampling your continuous time signal as this. So it is the same sampling at interval of sampling interval of omega naught, but this sampling is in frequency. So you can get discrete Fourier transform by sampling discrete time Fourier transform or Z transform of your signal. So second thing is your signal, original signal h of n, for which you are calculating discrete Fourier transform, it is aperiodic. And you want to save its samples. So here number of samples are 21. Here number of samples are around 1 million or 6 million. So you can calculate, you can save the sampled version of this Fourier transform. Let us further understand it with the help of an example. For example, you have a signal x of n, which is just a rectangular waveform in discrete time. Now if you make it periodic with period 5, then it is a periodic signal, it is a periodic signal. You can calculate its discrete time Fourier series, which was periodic with period n. So you can see here, this is periodic from 0 to 4, then 5, this is being repeated. This discrete series, discrete time Fourier series is periodic in frequency, whereas this dotted curve is discrete time, discrete time Fourier transform, which you have studied in chapter number 2. But here, if you calculate its of 5 length sequence, n is equal to 5, then you will have a discrete from 0 to 4, and it has same length, n is equal to 5. So instead of saving this continuous spectrum, you can save these 5 samples in your computer to represent the Fourier transform of this continuous discrete time signal. Now let us define discrete Fourier transform. As I have just mentioned, you can get discrete Fourier transform by sampling discrete time Fourier transform. So as you know, it is equal to, you have studied in chapter number 2, minus infinity to plus infinity x of n e raised to power minus j omega n. And here you have a sequence x of n which has a range from 0 to n minus 1. You have x of n a n length sequence. So here n is 0 to n minus 1. So this will become n is equal to 0 to n minus 1 x of n e raised to power minus j omega n. So now uniformly sampling x of e raised to power j omega on the omega axis between 0 to 2 pi at omega is equal to k omega naught is equal to k 2 pi over n for k is also between 0 to n minus 1, as we have just seen here. If you have 5 length signal, its discrete Fourier transform is also of n is equal to 5. So if you have n length sequence in time, its Fourier transform x of k will also be of length n. So putting this expression here, what you will get is omega is equal to k into 2 pi over capital N. And from this equation your discrete Fourier transform x of k will become summation from 0 to n minus 1 x of n e raised to power minus j two pi over n into n. This 2 pi over n is the value of omega, and you are sampling it uniformly sampling it at k omega naught. So slightly rearranging it, what you will get is n is equal to 0 to n minus 1 x of n into e raised to power minus j 2 pi over n into k n. This k I am bringing it outside this bracket, so it will become x of k is equal to summation n is equal to 0 to n minus 1 x of n w n raised to power k n. Here this w n is equal to e raised to power minus j 2 pi over n. So this is your expression of discrete Fourier transform. So using the same approach, you can prove that from inverse discrete time Fourier transform, you can prove that this x of an inverse discrete Fourier transform is equal to 1 over n summation k is equal to 0 to n minus 1 x of k w n raised to power minus k n. This is inverse discrete Fourier transform. You can write this expression in matrix form also. Say for example, as you have discrete Fourier transform equals x of k n is equal to 0 to n minus 1 x of n w n raised to power k n. So for k is equal to 0, x of 0 can be written as summation n is equal to 0 to n minus 1 x of n w n raised to power 0 into n. So you can expand it like n is equal to 0 to n minus 1 x of n into 1. This w n raised to power 0 is 1, so it will become x of 0 plus x of 1 plus x of 2 plus so on to x of n minus 1. This is your x of 0. Similarly, for k is equal to 1, your sample of discrete Fourier transform at k is equal to 1 will become w n raised to power 1, which is k, into n. So it will become equal to n is equal to 0 to n minus 1 x of n w n raised to power n. So x of 1, x of 0, w n raised to power 0, actually it is 1 into 0 plus x of 1 w n raised to power 1 into 1. Here you have actually 1 into 1 plus x of 2 w n raised to power 1 into 2. Here this 1 is representing k and this 2 is representing n, plus so on to x of n minus 1 w n raised to power 1 into n minus 1. This is the limit of this summation n minus 1. Similarly, for k is equal to 2, the expression will be equal to x of 0 w n raised to power 0 plus x of 1 wn raised to power 2 into 1 plus x of 2 wn raised to power 2 into 2 plus so on to x of n minus 1 wn raised to power 2 into n minus 1. So doing same thing for k is equal to n minus 1, please correct it, it is capital X of 2, and here for k is equal to n minus 1 you are calculating x, capital X of n minus 1, and it is equal to summation n is equal to 0 to n minus 1 x of n wn raised to power n minus 1, which is k, into n. And if you expand it, this x of n minus 1 will be equal to x of 0 wn raised to power n minus 1 into 0 plus x of 1 wn raised to power n minus 1 into 1 plus x of 2 wn raised to power n minus 1 into 2 plus so on to x of n minus 1 wn raised to power n minus 1 minus 1. So I am rewriting all the equations here. Here you have wn raised to power 0 into 1. Similarly here you have wn raised to power 0 into 1. Here actually you have 0. Similarly here you have wn raised to power 0 into n minus 1. So if you can see, you can write it in matrix form. This is your vector capital X, which is representing discrete Fourier transform. I can write it like here, X, which is this vector, into a matrix which is equal to 1 1 1 up to 1, and here again we have 1 for k is equal to 1 1, and it is wn raised to power 1 into 1 wn raised to power 1 into 2 up to wn raised to power 1 into n minus 1, and here we have wn raised to power 2 into 1. Here we have wn raised to power 2 into 2, and so on up to wn raised to power 2 into n minus 1, and it keeps going. It is 1 wn, this thing, raised to power sorry, this one, wn raised to power n minus 1 into 1, wn raised to power n minus 1 into 2, this term, up to wn raised to power n minus 1 n minus 1. Into x of 0, x of 1, x of 2, x of n minus 1. So this matrix is represented with dn. I am representing this vector x, which is your time domain signal, and this is your Fourier transform capital X. So in matrix form, you can represent your discrete Fourier transform like this. So if you want to calculate the inverse discrete Fourier transform, you can prove that it is equal to dn inverse x, where this dn inverse is equal to, this is dn, equal to 1 over n dn conjugate. Now let us do an example so that we can understand the utilization of these expressions. For example, you have a signal g of n is equal to 1, 2, 0, 1, and you have another signal h of n, it has 2, 2, 1, 1, and you want to calculate its discrete Fourier transform. So here n is equal to 4, your wn will be equal to e raised to power minus j 2 pi by 4. So your g of k will be equal to summation n is equal to 0 to n minus 1 g of n wn raised to power kn. So it will become g of 0 wn raised to power 0 plus g of 1 wn raised to power 1 plus g of 2 wn raised to power this is 1 into k, this is 2 into k, because we are summing over n, plus g of 3 wn raised to power 3k. So here g of 0 is 1, 0 is 1, plus g of 1 is 2 wn raised to power k, plus this is 0, I am not writing here, so just g of 3 is 1 into wn raised to power 3k. So using this value w of 4, we can have g of k equals 1 plus 2 into e raised to power minus j pi by 2k plus 1 into e raised to power minus j 3 pi by 2k. So as you know, your k is also from 0 to 3. It means your discrete Fourier transform must be also of length 4. So g of 0 will be equal to, if you put zeros in k, your g of 0 will be equal to 4. Your g of 1 will be equal to 1 minus j. Your g of 2 will be equal to minus 2, and your g of 3 will be equal to 1 plus j. Now if you want to use this matrix to calculate your discrete Fourier transform, for this signal, first you will have to write d4. So using above matrix, it will be equal to 1 1 1 1 1 1 1 minus j minus 1 j minus 1 1 minus 1 j minus 1 minus j. So if you multiply this matrix with 1 2 0 1, what you will get is, here you have g, what you will get is the same answer, 4 1 minus j minus 2 and 1 plus j. Similarly, if you find the Fourier transform of h of n using the same matrix, your h of k will be equal to 6 1 minus j 0 1 plus j. I will use these g and h later in some other lecture. Now if you want to find the inverse discrete Fourier transform, what you will need is, you have to find this thing, which is equal to 1 over n dn conjugate. So this is your dn or d4. If you take its conjugate, it will be equal to 1 by 4 1 1 1 1 1 j minus 1 minus j 1 minus 1 1 minus 1 1 minus j minus 1j. So if you multiply this thing with this matrix, you will get your original signal h of n. So this is end of today's lecture. Today we have defined discrete Fourier transform. In the next lecture I will explain its properties. If you have any question, you can send me an email. Thank you.